The Stefan-Maxwell equation is a very important equation in engineering. It helps us find the relationships between multiple components in a system, in a binary system. So let's look at each component of this equation and determine what it's trying to tell us. Right here we have our x of I, and these are all components. This is a mole fraction of a component. The next part of this equation is our gradient that you can tell because of the upside down triangle. And this gradient is the driving force of our equation. It's the gradient of chemical potential of I. You should recognize this D as the diffusive coefficient, but this diffusive coefficient is specifically for the diffusive coefficient from I to J. And this would be found on the line, on a line. Right here, we have our concentration, and that's just going to be, C is going to just be our concentration of all the components. Components. That's molar. Our final part of this equation is our molar flux. This is going to be our molar flux of A, component A. So from here, there are multiple different kinds of Stefan-Maxwell equations, and one includes one with the velocity, and that can help us a lot in future problems. So what we're going to do now is we're going to relate our molar flux equation to the Stefan-Maxwell equation with the velocity. Before we continue, I do want to mention that for our mole fractions, you can use either y or x to describe your mole fractions. For liquids, you usually describe those mole fractions as x, and for our gases or our vapors, that mole fraction is going to be a y. In chemical engineering, a lot of the times you use, or in heat mass transfer, I should say, a lot of the times you use the mole fraction for a gas, so we typically use y. In the rest of this problem, we are going to be switching out x for y, but it means essentially the same thing just for a gas. I'm also going to label this part of this equation as the driving force of I, just for simplicity. So we have our driving force of I is equal to the sum n when j equals 1 of our mole fraction I times our molar flux of component A minus our mole fraction of J times our molar flux of I over our concentration times our diffusivity coefficient of I, J. Now let's write down the other equation including velocity. We have the same beginning, but this equation is different. So we have our mole fraction of I and our mole fraction of J, multiply that by the velocity of J minus velocity of I, all over our diffusion coefficient of I, J. These two problems together, we want to make sure that they have all the same components. And one thing that the velocity equation is missing is this concentration right here. So let's multiply both the numerator and the denominator of our velocity equation by C. If we expand that out, we get that our concentration multiplied by the mole fraction of yi, or mole fraction of I, mole fraction of j, times the velocity of j minus the velocity of I over concentration times diffusive coefficient of ij. Let's further multiply this out. So we'll multiply all of these, and we get that the sum from j equals 1 is y c is y I c j v J minus Yj Civi all over Cdij. Now I'm saying a lot of things, and let's make sense of this again. Y sum fraction C is the concentration of all the components, V is the velocity, and D is the diffusive coefficient from I to J. You'll notice that this equation looks rather similar to what's going on here. Now, we have the concentration on the bottom, we have our two mole fraction components of Y and J, but we don't have our N yet. So let's make an analogous representation. Our Nj is equal to the concentration multiplied by the velocity. And our Ni is the same thing, just with respect to I. So if we substitute that into our equation, we get the revelation that our velocity versus our molar flux equation might not be so different. And look at that, the exact same equation right here and right here. Well, what if we want to put this equation in terms of the diffusive flux? Great question. From previous videos, you need to understand that the molar flux, say of J, is equal to the diffusive flux of J plus the mole fraction J times the entire molar flux. And let's substitute that into this equation to find the diffusive flux with the Stefan-Maxwell equation. So we're going to transform that. We get the sum J equals 1. And remember, you can just substitute this J in for I if we want to change it to the I part of the equation. So our mole fraction of I times our diffusive flux of J plus mole fraction of J times the total flux. Put that over here, but in terms of I, all over concentration times our diffusive coefficient. We also want to relate concentration into this problem. So we realize that we just put concentration right there into our equation, plug it back into the Stefan-Maxwell equation, and then multiply this out. And the intention of multiplying this equation out is to cancel out certain parts that we don't necessarily need, or to find a new identity that we might not know about. Minus Yj all over concentration diffusivity coefficient. So you can already see that these two parts cancel each other out, and we get the equation that's very similar to our molar flux equation. Oh my gosh, I just keep making mistakes. It's very similar to our molar flux equation. Look right there, you see how our molar flux is the exact same, just replaced with a J. Going back to the Stefan-Maxwell equation, we can also relate our gradient of chemical potential, and if we assume that the chemicals or components we are working at are similar to a pure state, we might be able to take our Stefan-Maxwell equation, equate it from the pure state to the state we're working in, and see what that goes down to. So here's our blank Stefan-Maxwell equation, and we're talking about having our chemical potential of I equivalent to chemical potential of I at a pure state, or standard state. But it's not always going to be at standard state, so there must be a way to have an equation that shows that there's something added onto the pure state, or subtracted, that changes it into the current state we're at. And that's true. If you add on coefficient times temperature multiplied by natural log of the mole fraction of I, you get the actual state of our chemical potential. And what this really does is just say that there's something that's accounting for the fact that nothing's in a pure state all the time. Now we want to find the gradient of our chemical potential, and it's going to be the derivative of, with respect to z, the distance we're going. So let's plug in our chemical potential, RT natural log xi over dz. This part of the equation is simply saying that there's something else going on with our standard state that's adding it onto it that makes our true state not the same as our standard state. So from here, we can find our gradient of our chemical potential, like in the Stefan-Maxwell equation right here. That's going to be equal to the derivative of our chemical potential with respect to distance. So plugging in the equation we just created from our pure state, we get this to derive from our chemical potential becomes 0, and we get T of 1 over xi, the derivative of xi, our mole fraction of I, with respect to dz. From here, we can plug our equation back into the Stefan-Maxwell equation. So take this and plug it in for our gradient of our chemical potential. We get our mole fraction of I multiplied by our RT times 1 over mole fraction times the derivative over RT. And this equals the same right side. So the right side is going to be identical to the original Stefan-Maxwell equation. So from here, let's cancel out our units. And in the end, we just get that the derivative of our mole fraction over with respect to dc is equal to the sum xi, our molar flux minus our fraction of J times our molar flux over concentration times the diffusive coefficient from I to J. So how are we going to show this, that for a pure component, this equation simplifies down even further? Well, from before, we know that this equation out for molar flux is equal to the diffusive flux. And I'm going to take that, I'm going to replace our molar flux with our diffusive flux. So what we're going to get is we're going to get this lovely equation that we can simplify down even further. How are we going to do that? Great question. Now that we've replaced this equation, we want to do the equation for a pure component. And we'll start by doing that by saying this is equal to driving force of I. Just replace that whole part. And we'll also say that I is equal to 1 and J is equal to 2. So because this is a sum, we'll have to add 1 to 2. We'll start by doing 1. So the mole fraction of 1 multiplied by the molar flux of 1 minus the mole fraction of 1 times the molar flux of 1 over concentration times the diffusion coefficient of 1 plus mole fraction of 1 molar flux of 2 minus mole fraction of 2 times the molar flux of 1 all over concentration times our diffusive coefficient of 1, 2. This side of the equation goes to 0. So these two cancel each other out. So our final equation for now, we have our derivative of our mole fraction 1 with respect to z is equal to mole fraction of 1 times our molar flux of 2 minus our mole fraction, our diffusive flux minus our mole fraction of 2 times our diffusive flux of 1. All over concentration times our diffusive coefficient of 1 to 2. From here, we know that 1 is equal to y1 plus y2, or molar fraction of 1 plus our molar fraction of 2, because they have to be equal 100%. We also know that a diffusive flux added together, so J2 plus J1, has to equal 0. So 1 minus y1 must be equal to y2. Our molar fraction, our 1 minus one of our molar fractions has to equal the other molar fraction. And negative of our diffusive flux of 1 is equal to our diffusive flux of 2. Plugging that in, we get that y, our molar fraction of 1, times negative flux, diffusive flux of 1, minus 1 minus molar fraction of 1 times diffusive flux of 1 over concentration times our diffusive gradient. We're just going to make this minus J1 plus 1y1. These cancel out. That's over concentration times our diffusive coefficient. So our final answer is that our diffusive flux over concentration times our diffusive coefficient is equal to this derivative. And if we actually multiply everything over, we find that this is actually Fick's law. I know, funny, isn't it? So that's how the pure component simplifies. Our Stefan-Maxwell equation simplifies down to Fick's law for a pure component. And of course, Fick's law is negative. So the Stefan-Maxwell equation, what it does a great job at is it tells you how each component reacts or interacts with one another. And if you have a system with multiple components, you can use a Stefan-Maxwell equation to relate each component to one another and find out how they're all going to react with each other. So then you can change the system in order to make sure that it is exactly what you want it to be, or resulting in the final product or whatever you're making, for that to be exactly what you want.